So welcome to the Picture Language Seminar. We have a hiatus now because of all the other activities going on at Harvard, but we have a special talk today. We'll plan to resume this seminar on a regular basis in April. We're so happy today to have Jacob Fox. I first met Jacob when he was a high school student participating in a program here. He then was an undergraduate at MIT, graduate student at Princeton, and has done many famous things in analysis and combinatorics. He's professor of mathematics at Stanford University. He's going to tell us today about subset sums, and we're very pleased to hear what you're going to teach us. So Jacob, the floor is yours.
Thanks, Arthur. Let's see. Well, thanks a lot for the invitation. I've given a few hundred talks before, but this is probably the first time in a physics department. And so everyone here has some amount of, is a mathematician to some degree, so hopefully that's fine and we communicate. Well, please ask questions if something's unclear. And so most of this talk is really about combinatorial number theory and some classical questions and some answers there. Some of the people here are interested in quantum mechanics and the mathematics of it, and connections to quantum computation. And I'll mention a problem a little bit later that's of interest from the computational perspective around subset sums. Great. So some classical problems and results in number theory are about representing integers as the sum of elements from some special set or sequence of numbers. One famous example that's still open is Goldbach's conjecture that every even integer at least 4 is the sum of 2 primes. And there's positive theorems along these directions, like Gauss's Eureka theorem, that every positive integer is the sum of 3 triangular numbers, or Lagrange's 4-square theorem, that every positive integer is the sum of 4 squares. And there's the more general Hilbert-Waring problem, which is not completely understood yet, about sums of integers represented, integers representable as sums of higher numbers. Each of these are about representing integers as a bounded number of elements from some sequence. And today we'll be mostly focused not on that, but allowing for any number of elements from your sequence to add up. So general subset sums, so no condition on the number of terms. So let A be a sequence or set of positive integers. And we're going to denote by sigma of A the set of integers which are representable as a sum of distinct terms from A. So we're going to look at some basic questions here. A is said to be complete if every sufficiently large integer is in sigma of A. And it's entirely complete if every positive integer is in sigma of A. Then you can represent every positive integer as a sum of elements from A. And the study of complete and entirely complete sequences go back, one could say, thousands of years. For example, if you can represent every integer in base 2, which is equivalent to saying that the powers of 2 form an entirely complete sequence. On the other hand, this is rather fragile. If you delete any element from the powers of 2, you've just destroyed this entirely complete, and it's not even complete anymore. So if you get rid of the element 1, then you can only represent the even integers. So there's this fragileness here. And Sprague in 1947 proved that the perfect kth powers is a complete sequence. Now, one might think that this actually just follows from the Hilbert-Waring theorem, and it's almost follows, but in the Hilbert-Waring theorem, you're allowed to repeat perfect kth powers, and here you're not. So you're taking distinct subset sums. And another nice example due to Birch from 1959 is if you have co-prime integers, P and Q, least two, and you take the perfect p powers times the perfect q powers, that forms a complete sequence. So it's a pretty sparse sequence, and it was shown by Birch to be complete, and it's a constructive proof, so you can show how to construct every sufficiently large integer. So clear what these notions are? Okay, so now some of these are rather sparse sequences, but the even numbers is not complete. That's a rather dense sequence. It's half the integers. And so for modularity reasons, it can be the case that a sequence is not going to be complete. So a sequence could be possibly too sparse. So for combinatorial reasons, you can't represent integers. Another natural constraint is modularity issues that come up why a setup might not be complete. Now there's a simple characterization of entirely complete sequences due to Ron Graham. So a sequence is going to end up being entirely complete if and only if the smallest element is 1. And the kth element is at most the sum of the previous elements plus 1. This has a very simple proof. In one direction, if ak minus 1 is bigger than the sum of the previous elements, then ak minus 1 is not a sum of elements from A. Indeed, if you take a sum of elements that are HAs where J is less than your K, then it can't add up to AK minus 1. On the other hand, if you add any element bigger than AK, or AK or bigger, then you're going to be too large. So you just can't represent AK minus 1 in that direction. And then in the other direction, you can prove by induction on K that when you take the first K terms, the subset sum, sigma of the first K terms, is going to be the entire integral from 1 to the sum of the HAs from J equals 1 to K. And the proof is by induction, so if you know it's true for K, now you're allowed to add an AK plus 1. That's just going to shift that entire interval by AK plus 1. And by our assumption about AK minus 1 not being too big, these intervals will overlap, and you will get everything from 1 all the way to the sum of the AJs from J's 1 to K plus 1. This is a very simple theorem about entirely complete sequences. Unfortunately, there's nothing like this for complete sequences, so it makes it more interesting. There's no nice characterization. Now, this idea that was used in this proposition also can be extended rather easily to this lemma of Graham, that if you already can represent all the integers in an interval from x to x plus a, and then you're adding in an additional element a, you can extend that integral by adding a, because now you can represent that interval from x to x plus a, plus you can represent the translate by a, and the union will overlap, and so you'll have this entire interval from x to x plus y plus a, and then you can recursively apply that, and not only an interval from x to x plus y, but if the AIs don't grow too quickly, then you can get a much longer interval where you can add the sum of the AIs, adding these elements to your sequence. Okay, so if you get a fairly long interval and your elements that you're adding in don't grow too quickly, then you can just keep extending it and get everything further on. So kind of the first thing is trying to get a long interval and then add additional elements. Great. Okay, what about complete polynomial sequences? So we have a polynomial in one variable, and then we're going to let A be the values when you evaluated integers, positive integers, and then there's some necessary conditions for the sequence A, the values when you evaluate the polynomial of positive integers, to be complete. First, the leading coefficient of this polynomial has to be positive. Otherwise, there's only a finite number of non-negative values, and so you can't represent the positive integers. Another thing that has to happen is for every prime p, there has to be at least an n such that p does not divide p of n. Otherwise, you just won't be able to represent the things that aren't a multiple of p. So, so these are two rather simple necessary conditions, and it turns out that these necessary conditions are sufficient. This was proved by Roth and Sakharich in the late 1950s with an analytic argument. And then there was another proof by Castles using the circle method. And there's a simpler combinatorial proof that even extends a little bit further by Ron Graham a few years later. You can represent every polynomial. Now, for this theorem, it's a little bit more general because he allows for the polynomial to have real coefficients. You don't have to have integer coefficients. But you can represent every polynomial as a sum of binomial coefficients with coefficients in front of these binomial coefficients. So x choose k is the polynomial of degree k that you get. And so if you have this p of x, you can represent it uniquely in this form where p is a degree k polynomial. And his characterization is A is complete if and only if the leading coefficient alpha k is positive. These alpha i's have to be rational, represented as pi over qi, with the greatest common divisor of the numerators being 1. So these pi's and q's are supposed to be integers here. Great. So this is complete polynomial sequences. And unfortunately, as we saw for the powers of 2, it has this rather fragileness that you delete one element and it can completely destroy completeness. And so Erdős was interested in trying to come up with more robust notions of completeness, where if you kind of did something to the sequence that you still keep it complete in a sense. And so this is, Erdős and Burr introduced the notion of Ramsey complete sequences about 40 years ago. And so we're going to let A of n be the number of elements in the sequence A up to n. So this is the interval from 1 to n. And we say the set for sequence A is R Ramsey complete if, however we partition the set A into R subsets, every sufficiently large integer is in the union of these sigma of AIs. Now, that sounds a little bit complicated. What it really means, if you think about it, is you give each of the elements of A one of R colors, so you're coloring every element of A, and you're able to represent every sufficiently large integer as a monochromatic subset sum. So in some color, you can represent it as a sum of elements of A. And this notion is rather robust. The reason why we have this union here is that it's not true if we try to get that one of the AIs is complete. And the reason for this, even in the case R equals 2, you could color everything from 2 to the 2 to the I to 2 to the 2 to the I plus 1 and color red for I even, and otherwise color it blue. And you can check that not every both in red and blue, you want there'll be infinitely many elements that you can't represent as a monochromatic subset sum. And so this is the right notion where for every sufficiently large integer, there exists some color for that integer. We could write some sum from that color. And there are rather sparse sets that are 2 Ramsey complete. So what Burr and Erdős were able to prove is that there's a 2 Ramsey complete set A, where up to n, there's only log n cubed elements. And they use construction, basically elaborating on the fact that powers of 2 are a complete sequence to do this. Their proof only works for 2, so it doesn't give anything for more colors. And they get only log n cubed elements. And then they get a lower bound, which is a constant times the square of log n. They don't actually, they didn't write this proof up. They said it was too challenging to write up, so they wrote down a weaker result and then said it's possible to prove this, but it's pretty difficult to write up. And so they asked several questions that remained open for a long time. They asked to improve these bounds for the 2-color case. And then for more colors, there wasn't any bounds, and they wanted to prove that there's a somewhat sparse R Ramsey complete sequence for R greater than 2. And so they didn't even know if there was a sequence that had only n to the below 1 element, so below any power of n R bigger than 2. And then also they wanted to determine which polynomial sequences are R Ramsey complete. So we knew the complete polynomial sequences, which ones are R Ramsey complete. And Erdős was very interested in these problems. He asked them in this paper later, which is a collection of his favorite problems, and he even offered some prizes, which he had a tendency to do this. So the one of the main results I want to tell you about today is a result which solves all these questions. So we can tell you that result. So first, we'll answer the first two questions and then generalize it. So the first theorem tells you, very similar to the lower bound, there is an R-Ramsey complete sequence A with only log n squared times something that, depending on R, which is linear in R, elements up to n for all n. And so this has this robust notion. And also more generally, if A is R-Ramsey complete, then you have a lower bound that matches the upper bound for all large n. So that's the right growth rate. And we have a proof that's short enough that one can actually write it down. So that's written down in this paper. But also for polynomials, there's an analogous result. So if you have a degree D polynomial, and now it has to be complete for it to possibly be R-Ramsey complete, because one Ramsey complete is equivalent to being complete. Then there's a subset A, which is actually really sparse. So it's only up to n, it has about log n squared elements. And it's going to be R-Ramsey complete. And so you can solve all the problems with this theorem. And one simple corollary of this is if it's actually complete, then it has this robustness for polynomial sequences. So if a polynomial sequence is complete, then it's R-Ramsey complete for all R. So that characterizes the Ramsey complete sequences. Any questions about this? I want to give some ideas about the proofs that go into this, and then to talk about some related problems and ideas around subset sums. So let's try to prove that first theorem, or at least sketch the proof. So the main key lemma for the proof, is the following. So this is going to be the key lemma. It's going to easily follow this theorem from the key lemma. So the key lemma says you're given an epsilon between 0.5 and an n which is sufficiently large. Then you can find a subset, which we're going to denote S sub n, of the interval from n to 2n. So it's a set of integers between n and 2n. It's not that large, so it has some constant over epsilon times log n many elements up to n, between n and 2n. And whenever you take a subset of this set with at least an epsilon fraction of the set, then you have this really long interval from yn to 3 times yn in the set of subset sums of your A5. And this yn here is going to be some constant times n log n. Okay, so that's the key lemma. How does it imply the theorem? So there we can prove that in the rest of the slide. So we're going to apply the key lemma with epsilon being 1 over r and n equals 2 to the I for each I that's sufficiently large. And let A be the union of these S sub 2 to the I's. And this sequence A you'll get now has up to n, at most some constant times r times log n squared elements. You're taking the union of these subsets of these dyadic intervals. And then now let's consider an R coloring of the set A. So each element we're going to give it one of R colors. No matter how we do that, we're going to pick AI to be the subset of S2 to the I of the elements of the most common color inside that interval, 2 to the I to 2 to the I plus 1. And now AI is going to have density at least 1 over R within S sub 2 to the I. And that's just because we have the pigeonhole principle. So one of the R color classes will have at least a 1 over R fraction of the elements. And then by the key lemma, we know that everything from yn to 3yn is going to be inside of, it's going to be representable as a subset sum inside that AI. So all the elements from yn to 3, from y2 to the I to 3y2 to the I will be, so the entire interval will be representable as a subset sum from AI. Now these intervals, they're going to be overlapping eventually. And the important thing to make them overlapping because of the y sub 2 to the I is that 3 is bigger than 2. And that this yn is not that much bigger than n sin log n. Okay, so you'll be able to cover every single sufficiently large positive integer as a monochromatic subset sum using this. And then the rest of the proof then is in proving the key lemma. So this completed the proof of the theorem, assuming the key lemma. And how do you prove this key lemma? And so, as is common in combinatorics, we use the probabilistic method. So we're not going to create the set constructively, the set Sn. We're going to pick it at random. So we're going to build it at random. The problem, though, is that if you pick it uniformly at random, about half the elements are going to be even. And if you let A prime be the even elements in Sn, then you're only going to get even elements in the subset sums. So you're not going to be able to get the whole interval. So there's possible modularity problems that happen. So we need to make sure that most of the elements of this set are not multiples of 2. Most of the elements are not multiples of 3. Most of the elements are not multiples of 5, etc. So we need to make sure that we don't have too many small prime factors. So that's the point here. So we're going to pick just uniformly at random of this particular size, so that no element of this set Sn has a prime factor less than log n over 2. The log n over 2 is not an important number. There's a lot of slackness argument, but it's a probabilistic argument. And then the key part to proving this lemma is that with very high probability, a random set A prime from n to 2 n of the size 4,000 log n, because we've lost this factor epsilon, and each element has no prime factor less than log n over 2, satisfies that you're going to actually have this long interval in the set of subsets. And the key thing here is that very high probability is very high probability. It's so high that we can union bound over all of the subsets of our set Sn of size epsilon as Sn. And so this will happen with very high probability, close to 1. And so that ends up working out. And roughly what happens is you add the elements one at a time. And at each step, it's very likely that you're going to grow. So if you add one element to a set, often you'd expect the set of subset sums to double in size unless there were some added correlations. And you just keep careful track. And you do this for a long time until it gets pretty large. And you have to add things together in a way that will allow you to get an interval, and then you can grow that interval longer. Yes. Yes, so I'm not going to go into the details of that because, but I just tried to sketch the idea that you try to add
expectation.
What?
Is it by computing the expectation?
You at each step you're adding an additional element from your 4,000 log n, and you just show each time you're very likely to grow in the beginning. In terms of the set of subset sums, it's going to basically be like a power of 2 for a while. And it's very unlikely that you'll have some additive structure there. And then toward the end, you do something different. And so there's a general recipe. This is part of a paper that's over 70 pages long. And so I'm not going to go into the full details here, but I wanted to give some flavor of the idea. So this is this general recipe that ends up working for many problems. That we have. So the first idea is we start off with a set A of integers, and it's not a general set in that you have to be careful. You like to find a long interval in the set of subset sums of A. If A consists only of even integers, then you can't do that. So you need to make sure that there's, for any prime P, there's a lot of elements that are relatively prime to P. So there's some constraint there. And then you arbitrarily, or rather just randomly partition A into L subsets. L often is a constant for us, but it doesn't always have to be. And you do this so that they're the same size. So they're all roughly 1/L fraction of A. Usually A will be a finite set for these applications. And then we're going to partition each AI into a BI and CI so that the set of subset sums modulo each C. So if you look at the set of subset sums of BI modulo each element in CI, it's fairly large. And so there's a way to do this, but if A comes at random, then it's very likely to hold, that this will hold. And then using this previous step, you have to show that the set of subset sums of AI, which is the set of subset sums of BI and CI, is large. And finally, using that the set of subset sums of each AI is large, you can basically glue them together to get a long interval. And so I'll just say a little bit more about going from step 2 to 3 and 3 to 4. So the idea of going from step 2 to 3 is very simple. The main claim here, and it's very simple again, is that if you have a positive integer C and a set B of integers with C naught and B, and the size of sigma of A considered modulo C is at least some number H, then when you add C to A, you get at least H additional elements in the size of the subset sum. And if you look at each congruence class, mod C, and you see at least H congruence classes, well, by adding C, you're going to see at least one more additional element in the set of subset sums. So this is just a very simple claim, but it turns out that this is enough for some of the applications. And the second lemma, which is really helpful to going from 3 to 4, is that if you have these sets A1 to AL, and there's some conditions here on these numbers, and each AI is at least some value n, and is a subset of an interval of length q plus 1, and L is large enough, and none of these AIs is a subset of an arithmetic regression of common difference greater than 1, which is related to this issue about modularity earlier. Then when you take the set of the sum set of these L sets, you're adding one element from each of these AIs and doing this over all possible ways of doing that, that set contains an interval that's pretty long, of length at least L times n minus 1 plus 1. This is a nice lemma of Lev, and there's variations of this lemma that have been proved earlier. And so this is a way of going from the AIs having large subset sum to actually and lying in some interval to actually getting entire intervals in the set of subset sums. Okay, so these are a little bit of tools here, but I'm sweeping a lot of the details under the rug there. Yeah. Okay, so this was a Ramsey type result that we saw earlier about coloring. It's natural in combinatorics to look at Ramsey theory to look at density type results, which often will be stronger. So a famous example of this is about 100 years ago, van der Waerden proved this theorem that if you R-color the positive integers, there's going to be one of your color classes that have arbitrarily long arithmetic regressions. So we'll have some nice patterns in at least one of your color classes. These long arithmetic regressions, arbitrarily long. And about half a century later, Semeretti proved a density strengthening of this, that if you have a subset of the positive integers of positive upper density, then it contains arbitrarily long arithmetic regressions. And why is that strengthening? Well, one of the R color classes will have positive upper density, at least 1 over R. And so that's a density type theorem. And it's very natural to consider density type questions here. So this was not considered before our work, but it turned out to be quite natural to look at. And so we say a set A is epsilon complete if whenever you take a subsequence, if A is a sequence, A prime, that contains at least an epsilon fraction of the elements up to n for n sufficiently large is complete. So whenever you take a dense subset, dense here means at least an epsilon fraction for n sufficiently large, then you get a complete subsequence. And then the first question is, one might wonder, is how sparse can an epsilon complete sequence be? So that you have this density property. And actually that's question 1, but question 0 should be, is there any epsilon complete sequence? The natural choice to think about is the positive integers, and that's not going to be epsilon complete for small epsilon, because you can take the even integers, and that's as your A prime, and that has at least half of A essentially, and won't be complete. But there are epsilon complete sequences for any epsilon greater than 0. The primes, for example, are known to be epsilon greater than 0. So if you take a dense subset of the primes, you'll necessarily be able to represent that with sufficiently large positive integer as a sum of elements from that set. And one might wonder, can you find much sparser epsilon complete sequences? And an epsilon complete set must satisfy some modularity and growth conditions. So for each prime p, the multiples in p can't be too dense, so they have to have some small density. And the second property is a growth condition that there's going to exist some positive integer c such that the kth element of your sequence has to be at most the sum of the first epsilon k plus c elements in your sequence. And the main result that we prove is that if you take a random sequence and it satisfies essentially the modularity and growth conditions, then it's almost surely going to be epsilon complete. So once you have the necessary conditions and you pick something at random, basically works for us. In particular, we have the following theorem. Consider a sequence of positive integers, increasing a sequence of f1 to ft are your starting elements of your sequence. You can pick them arbitrarily for some fixed t. T has to be at least 1 over epsilon. And the mth element of the sequence, you'll just pick to be the sum of the first epsilon m elements in your sequence for m bigger than t. So this is recursively defined sequence. The growth of this sequence is faster than any polynomial, but it's sub-exponential. It's a quasi-polynomial growth. And up with estimates for what this growth looks like. But it's in between polynomial and exponential growth. And if the set A is epsilon complete, you can prove that it can't grow faster than this sequence. And it turns out that any sequence that whenever you start off with f1 to ft, they're going to, like this, will be within a constant factor. And so this makes sense in terms of the growth rate. So you can't grow faster. And then there exists an epsilon complete sequence A where the growth is actually on the order of f of k for the kth element. And the idea is actually you can make it interlace. So the set A you pick is going to be, you'll pick a random element to be your kth element between f sub k and f sub k plus 1. And such that it has no small prime factor. Just pick a random element. And when you do that, you can show that it ends up working out here. So this is the key idea here. So basically you understand how sparse epsilon complete sequences can be. Now I'll end these parts about complete sequences with a conjecture that we don't know how to prove. So there was a theorem about BERT, which is the case R equals 2, or actually R equals 1 of this conjecture. So if you have R plus 1 pairwise relatively prime integers, the conjecture is that the sequence where you take the perfect powers of P1, P2 to PR plus 1 and multiply them, all the possible multiplications of these, is going to be a Ramsey R complete sequence. And it's not going to be Ramsey R plus 1 complete. And the reason is you can come up with a coloring that just works. So what we do is we assign each of these integers in the sequence a color j for which ij is non-zero and j is at most r. The ones that are left uncolored are just the perfect powers of PR plus 1. And that's a really sparse, it's an exponential sequence. It's very sparse. So most things can't be represented as a subset sum for this PR plus 1. And the powers of PR plus 1. And then you can check that this is, you're just not going to be able to represent all positive integers. integers. Sufficiently large as a monochromatic subset sum of this coloring. And yeah, so this would be a nice thing to do here. Another nice open problem here is all of our results earlier, positive results were based on random colorings and random sets. And, sorry, not random colors, but random sets. Or random sequences. And we don't know how to do these at all constructively. They really rely on union bounds. And so there's no constructive proofs here. It would be very nice to come up with some explicit examples that work nicely. Any questions about this?
The only previous results before yours were
Those were constructive, yeah. So Pham and Erdős had this result for 2 colors, and it was a weaker quantitative bound, but and it was based on putting together powers of 2s and some other things to get log n cubed elements up to n. So it was something by hand that works, but you know, we didn't learn too much from that, and it really works for some strong reason only for 2 colors. Yeah, great. So let me turn to another coloring type result. So before we were looking at complete sequences where we wanted to represent every sufficiently large integer. And here we just want to represent one particular number, n, as a monochromatic subset. So f of n is going to be the minimum r such that there's a way to r color the positive integers from 1 to n minus 1, such that no monochromatic subset sums to n. So let's see an example. F of 23 is at most 3. And this is a greedy color. So we're just going to color all the positive integers starting with 1 red until we can't anymore. And the numbers from 1 to 6 add up to 21. And so that's, you're not going to get 23 as a monochromatic subset. So, and then we'll keep doing this for the blue elements. You're coloring from 7 to 11. And you notice that if you add any 2 of them up, you get less than 23. And if you add any 3 of them up, you get too many. It's more than 23. And similarly from 12 to 22, if you add up any 2 of them, you add up to more than 23. So that's a 3 coloring that works. And the green coloring generally gives you about square root of n over 2 colors without writing n as a monochromatic subset sum. And Erdős was interested in what's the minimum number of colors you can use to color n. 3D gives this, but that's not near optimal. And Erdős first proved that the number of colors you need grows slower than n to the 1/3, and asked if it actually grows roughly like n to the 1/3 in terms of the exponent being 1/3. And this was later answered by Alon and Erdős. They proved Erdős's conjecture about this. So they have lower bounds and upper bounds that have n to the 1/3, and there's some divided by logarithmic factors here. In the lower bound, there's a log n to the 4/3. In the upper bound, there's a log n to the 1/3. And they wanted to understand how to close the gap between the lower and upper bound here. What's the truth? And they thought maybe the upper bound is closer to the truth on this problem. So there's a lot of logs here. And Van Vu later improved the lower bound from 4/3 to 1 in terms of the exponent of log n. Again, these exponents of logs don't match between the lower and upper here. And another one of the results that come out of this general techniques about subset sums plus some additional ideas actually solves this problem. So we determine f of n up to a constant factor. And it turns out that it's not as nice as these types of functions. It's not monotone or even close to monotone. There's a number theoretic function, the Euler's-Toten function that comes up. And so the truth is n to the 1/3 times n divided by Euler's Toten function. So that's a number of integers at most n that are relatively prime to n, divided by log n to the 1/3 times log n to the 2/3. So indeed, their conjecture was correct in the sense that the power of log n was 1/3, but there's some additional things going on here in terms of the number of log factors. So for most n over phi of n is like a constant. And if n has a lot of small prime factors, it can be as large as log n. So that's an upper bound on this. And when it's log n, so in the rare case that n has a lot of small prime factors, then the upper bound matches this value f of n. But for most n, it's a log n factor smaller is the truth here. And again, it's far from monotone because you can find two n values that are nearby, and one's prime, and one has a lot of small prime factors, and so you can easily be off by a factor of log n locally here. So I'll say a little bit about the upper bound. I'll explain what Alon and Erdős's coloring is that gives the upper bound. So what does this coloring look like? There's different types of colors. So there's the first type of color. So you use half the colors. The color J, you're going to use all the integers from the interval n over j plus 1 to n over j. So J will be going from 1 to r over 2. And that'll color all of the large positive integers. So everything bigger than 2n over r will get colored one of these r over 2 colors. And why does each color miss n as a monochromatic subset sum? Well, if you add at most j of the elements, it'll be less than n from this interval. If you add any j plus 1 of them, it'll be bigger than n. So that's one type. A second type of color class they use is for each of the first r over 4 primes p that do not divide n, you're going to color the multiples of p using one color. And then in each of those colors, you'll only get multiples of p for the corresponding p. So for example, if n is odd, one of those primes p will be 2, and then you would color all the remaining things that you haven't already colored. It's a multiple of 2 in this one color. Now, what remains is that there's not many uncolored elements left. They have to not be a multiple of these r over 4 primes. And also they can't be too large. And so they group together the remaining uncolored elements in 1 to n minus 1 into r over 4 colored classes, each with some less than n. And there's not so many elements left, and they're all pretty small, and so you can end up doing this. And for a number of theoretic reasons, this is R that will work out. So that's what we do. To get the tighter bound, one can do some more careful number theoretic coloring. So you just have to do something a little bit more carefully to color this sparse set of small numbers left. And so due to time, I won't go into the details of this. It's in the paper. It's also available on the slide. I'd like to see it. Okay. So there's another coloring that works that you can kind of play around with. So there were some old problems that Samarati and Vu answered about almost 2 decades ago about long arithmetic progressions and subset sums. So what their theorem is, and this was an old conjecture, is if you have a subset of 1 to n and it has at least some big constant times square root of n elements, then when you take all the subset sums, you'll get a really long arithmetic progression inside the set of subset sums of length n. And it turns out that this is a nice result, but actually for many applications, you want something stronger than just an arithmetic progression. You want something that's known as a homogeneous arithmetic progression. And so an arithmetic progression, so the first element will be a, the next will be a plus b, the next one will be a plus 2d, et cetera, all the way up to a plus k minus 1d. This is a k-term arithmetic progression. There's k terms in the sequence, evenly spaced out. It's called homogeneous if the common difference d divides the first element. And there's some natural reason why this is called homogeneous. And it was shown that if you add an extra log and underneath the square root, independently by Feynman and Sarkozy, that actually not only can you get an arithmetic progression here, sigma of a, but you can get a homogeneous arithmetic progression. So it's actually helpful for certain applications. And it had been long conjectured that actually you can remove this log n. And it's explicitly written in various papers, and this is a new result in our paper that you can get these homogeneous arithmetic progressions. In a follow-up work, we extended this, which I'll explain shortly. And use it to address another old problem in combinatorial number theory. So this is known as the non-averaging subset problem. So a set A of integers is non-averaging if no element is the average of some of the other elements of the set. And so there's a famous theorem of Roth that if you have a subset of 1 through n and there's no 3-term arithmetic regression, then the size of the subset is little o n, that it can't be a dense set. And that's saying that no element is the average of 2 other elements. And this is asking for something for a weaker property, or rather a stronger property, that no element is an average of not just 2 elements, but any subset of your elements. One wanted to know how large of a subset of 1 through n can you have that's non-averaging. And using the previous results on homogeneous arithmetic regressions, you can get an upper bound that's square root of n times log n. And there was a construction that looks a lot like the lower bound construction for Roth's theorem, this theorem we discussed earlier due to Baron, but it only works in some 2-dimensional sense, and there's some higher dimensional construction there that gives you a n to the 1/4 lower bound. So there's still a large gap here, and this large gap has existed for a very long time. This was this result from the early 90s, and it had improved some earlier results from the 60s and 70s. And so we have a new upper bound, which doesn't match the lower bound, so there's still a gap here. The new upper bound, there's an exponent of square root of 2 minus 1. And the key tool for this new theorem is a generalization of the previous theorem we had, which applies to even sparser subsets. So if you have a subset of 1 through n, and before we were saying it was going to be a constant times square root of n, now you're only saying it could be much sparser, it could be constant times n to the 1 over k. But then there's going to be some d less than k such that the set of subset sums contains something that's known as a proper homogeneous generalized arithmetic regression of dimension d. In the case of d equals 1, this is just a homogeneous arithmetic regression. In dimension d, it's basically a proper generalized arithmetic regression is going to be a projection of a box, a d-dimensional box onto the integers. And so there's going to be d different common differences. And it's proper, meaning that it doesn't intersect itself. And homogeneous means that is a natural generalization of what we have in the 1-dimensional case. So you'll get a large proper homogeneous generalized arithmetic regression in this theorem. So this is a natural generalization to much sparser sets. Okay. So finally, I want to mention a couple of further open problems here. This was this problem of Erdős. Erdős referred to as probably the first serious math problem he ever worked on. So this is 1931. He started studying this question. And it's almost a century ago now.
Is there a distinction between omega and O?
Yes. So these are commonly used in computer science, but omega is at least a constant times this, and big O is at most a constant times, and theta is both. Yeah. Right. Thanks. This is if you have a set of k positive integers with distinct subset sums, Erdős conjectured that ak has to be really big, at least a constant times 2 big. And a simple example where you do get this type of growth is the powers of 2. So all the powers of 2 have distinct subset sums. This construction was improved by a constant factor by Conway, and then later there were several improvements. The most recent was by Bowman, which was already a few decades ago. So it's so there's some better constant factor than half here. I don't believe this conjecture is correct, so I think it's false. I don't have a counterexample, but I had to wager, I would wager if it's disproved in the next decade. On the other hand, so what do we know? The pigeonhole principle implies that, well, all the things that are subset sums of A1 to AK are going to be less than K times AK. And there's going to be a 2 to the K different subset sums. They have to be distinct, right? So by the pigeonhole principle, 2 to the K would have to be less than or equal to K times AK. So the Kth element would have to be at least 2 to the K divided by. So this conjecture is off by a factor of K. And we really want to close the gap here. One of the early applications of the second moment method in the probabilistic method is a result of Erdős and Moser from the mid-1950s. And they improved the lower bound on AK from being divided by K to roughly divided by square root of K. And there's a factor 1/4 in front. And I'll sketch this proof. It's very nice. It's presented many places, like in Alon and Spencer book on the probabilistic method. And so the idea is to take a random sum of elements from your sequence. So you take epsilon1 times A1 plus dot 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 plus epsilon K AK, and each epsilon I is going to be in 0 and 1 with probability of half independently of the other epsilon J's. Okay, so you consider this random sum. And then you apply the second moment method. So you want to say that the variance is pretty small. And you can compute the variance. 4 times the variance is the sum of the squares of the AIs, which is at most K times AK squared. And then you can use Chebyshev's inequality. So that tells you that there's some decent probability that you'll be in an interval, let's say twice the standard deviation. And so when you apply that, and use the fact that any particular integer has probability at most 1/2 to the K as being represented as one of these sums, because each element appears at most once as a distinct subset sum. Then putting those together gives you this lower. So recently, with 2 graduate students, Quentin Dubroff, who's finishing up his PhD at Rutgers, and Max Xu, who's a PhD student of mine at Stanford, who was working with me at Stanford, and also sound. We proved the following theorem. If you have A1 to AK has distinct subset sums, then AK is at least the middle binomial coefficient. K choose K/2. And the floor of K/2. And so the middle binomial coefficient looks like this, except instead of a quarter, there's a square root of 2/pi. And there was many improvements on the 1/4 over the years. This is the best known bound. Actually, it was in a paper, it was, so one of the improvements was by Elkes, and then in a later paper, it was mentioned that Elkes and Gleason has a proof of the square root of 2/pi minus the lower 1. Here, so something like this asymptotically, but that was never public, so not sure happy with their proof. So that would Gleason and Elkes were here at Harvard, and we have 2 different proofs of this. Actually, the other proof doesn't quite give this; it gives this asymptotically. One proof uses Harper's vertex isoparametric inequality, and that tells us that if you have a subset of the Boolean cube with half the elements, then the boundaries of size at least the binomial coefficient, this middle binomial coefficient, and then you can use that. So it's a fairly short proof. You have to be careful here. And another proof uses again, we look at a random sum like this, and then we use the Berry-Yassine theorem. So that tells you if you understand some things also about the third moment, then you can get that the random sum behaves like it. Not only do you know something about the standard deviation, but you actually know it's close in distribution to a normal distribution. And so then you can apply what we understand about the normal distribution instead of just Chebyshev's inequality.
But the full Berry-Yassine, not just central limit.
Yes, so we use the Berry-Yassine, so we understand the third moment. And if it fails, then you actually get Erdős's conjecture. Erdős's conjecture, but what I said earlier is I still don't believe Erdős's conjecture, despite results in that direction. So either you get Erdős's conjecture and or a random sum behaves like the normal distribution. That's what this proof shows, and so that's how you can get this best. So it'd be interesting now, I think, to get beyond the factor squared of 2/5 inside of this. These are both short proofs, so it's there's 2 pages, the whole paper, plus page references. Okay, so finally, I promised just a connection to complexity theory, and there's just a famous problem there that if you're given a set A of positive integers, and then also a target sum n, the question is n in the set of subsets? This is a famous complete problem, and for people looking at quantum computation, there's algorithms that have been proposed that people believe might be better than just the classical algorithms that are quantum algorithms, solve exponential anytime. So it's this is a central question in some sense in computer science as well. And with that, thank you. Finish talking.
Well, thank you very much, Jacob. That was a beautiful talk. And we were looking for the connections to quantum information and quantum science. And this afternoon, we were talking about Fourier analysis and higher Fourier, and you didn't mention that in your talk. Are any of these results connected to that?
These particular results that I was talking about, there is a little bit of Fourier. There's no higher Fourier analysis. I did mention Samretti's theorem, and the best known bounds for Samretti's theorem were the original reason why Gowers developed a higher Fourier analysis. So getting good quantitative bounds for van der Waals' theorem and Samretti's theorem was an important part in the development of higher Fourier analysis.
Are there any other questions here?
Can you talk about again just the proof that you just said for you? Like you said that the variance of that thing was something, and then you use that to prove that the root k.
Yeah. So Chebyshev's inequality says that the probability that a random variable will deviate from the mean, the expected value, by more than lambda, which is some parameter you're allowed to play around with, times the standard deviation, which is the square root of the variance. This probability is at most 1 over lambda squared. So if you pick lambda to be 2, then as an example, then there's a 1/4 probability that you're outside of this interval when you take a random sum. So you have this interval which goes from mu minus, say, 2 sigma to mu plus 2 sigma. And with probability 3/4, your random sum is going to land in here.
Oh, I see.
But each particular integer will appear with a small probability. At most 1 over 2 to the k, because you're taking the subset sums are distinct. There's 2 to the k different subset sums. One of them being the empty subset. The rest of them.
So I guess the theorem is that like this AK has to be pretty big, and the reason it has to be pretty big is because like if you take a random sum, then it's like kind of in this pretty tight interval, and then or I guess the tightness of the interval is determined by the size of AK. Like so, I guess if AK, okay, that makes a lot of sense.
Right. So sigma was the square root of the variance. The variance would be upper bounded by k times AK squared. And so sigma is at most square root of k times
yeah.
k.
Okay.
And when you put that together, you get.
That's a more complicated questions. In this examples of complete sets, how many do you usually need to sum? How many terms do you usually need to use?
Great question. How much do you need to add up? And one might guess by the key lemma, it's usually logarithmic to get certain things. So then key lemma, you're going to be able to represent, so we have a subset of n to 2n. And we could represent anything which was a constant times n, log n to 3 times that value, as a subset sum when we getting from there. And since each element is on the order of n, we're only going to be allowed to use log n of them, and we have to use log n of them. So often it's log n and not a constant. So this tells us nothing about the sort of questions like Goldbach's conjecture and other sort of questions along those lines where you want to use a temporary elements. So it's a very different flavor than these, other questions that people studied for many years as well.
Are there any other questions? Are there any comments or questions from people online?
Let's see anything in the chat.
No, I don't hear anybody. Everybody is muted, but if you do have a question, you should unmute. Well, if not, we thank Jacob again for a very beautiful overview of the subject. Great to have you here.
We can see a lot of cases.